So it's my pleasure to introduce Daniela Saban. Daniela is an associate professor of operations, information, and technology at Stanford University's Graduate School of Business. Her research explores issues related to the design and operations of online marketplaces, including online matching markets and procurement platforms. Prior to joining Stanford, Daniela spent a semester as a visiting scholar at Simons at UC Berkeley. She received her PhD in DRO from Columbia Business School and holds a bachelor's and master's in computer science from the Universidad de Buenos Aires. On a personal note, Daniela chaired my defense committee and is perhaps to blame for me no longer having the benefits of being a student. And what I really like about a lot of her work is that it's a model for how to both say things that apply generally across platforms, but also provide specific implementable insight for specific platforms. And we'll let her go from here.
Oh, thanks a lot for the very kind introduction. I'm really hoping I won't disappoint you with today's work. So this is joint work with Ali Aouad. He is at London Business School. And as I say there in the slide, please do interrupt. Just feel free to interrupt at any time. It's work in progress. So any comments, suggestions, or anything that you have for us would be more than appreciated. Okay, so the motivation is given by, of course, this growing number of matching platforms that acts as intermediates between users. So you can think of Airbnb just trying to match, people who have a house to rent with people who wants to have temporary accommodation. Uber Freight matching, people who have trucks with people who want to ship loads, and dating apps, of course. The motivation for today is going to be closer to online labor markets, which are marketplaces that match freelancers with companies or individuals looking for freelance services. So it's estimated that roughly 35% of people in the US that are of working age did some sort of freelancing gig in 2019. There were over $100 billion spent globally in these markets. And these are pre-pandemic numbers, so I only expect these numbers to have gone up the last year. So some examples you might be familiar with are Upwork, who tries to match freelancers with some sort of technical skills with companies, Rover, who tries to match dog owners with dog walkers and dog sitters. And the one that I'm going to be using, for example, in this talk is going to be Design Crowd, or just one of these design marketplaces that matches designers with companies looking for some design service. So for example, for a new logo. And what I'm hoping to convince you in the next slide is that assortment optimization and more broadly display optimization plays a central role in these matching platforms. Okay, so how many of you have used Design Crowd? Upwork? Good. Airbnb. Okay, Airbnb, good. Let it be Airbnb. So if you have used Airbnb, you will realize that the flow process from the moment you go into the platform until the moment that you learn whether there's a good outcome or a match or not looks something like this. So you go to the platform, you specify some search criteria, you try to find something that you like. Then the platform shows you a bunch of options and you need to decide whether you like or not like each option. You form a subset of things that you like and then you contact them or you apply, or in the case of a labor market, you submit a CV. In the case of a design platform, you submit a logo. And then you learn the outcome. You learn whether your request or your application was accepted or not. If it was accepted, a match happens. And the key thing here in this process is that you don't really find in a vacuum. You specify some criteria and then the platform chooses what they're going to show to you. So just to be more concrete, matches are formed after a user sees an assortment of users on the other side of the market, requests to match with one of them, and the request is accepted. And as I said, this is not just for these design platforms, also applies to Airbnb and more broadly. And the question that we have is how to select these assortments. And why is this an important question? When if you see the match formation process, the only thing that it's under the control of the platform is what am I going to show you. After I show you this assortment, where a match happens or not depends on the preferences of the users involved. So whether a user will issue a match request or not, and whether that request will be accepted or not. Okay, great. But this idea of selecting optimal assortment has been very much studied in the literature. In fact, many of the people there have done a great job trying to understand this, and that is true. However, most of the work on online assortment optimization has been focused on retailing. So first, we know they consider brick and mortar stores. So you have a store and you need to decide which assortment of products to carry in your store so as to satisfy your customers. And more recent in online retail. So, you are working at Nordstrom.com. Every time a user visits your webpage, what are you going to show to them? However, let me argue that there's a key difference between retail and matching, which is one-sided versus two-sided preferences. So just to give you a concrete example, you go to Nordstrom, you're trying to buy a t-shirt. Nordstrom show you these two beautiful t-shirts. You like the blue one, you buy the blue one, that's great. A transaction happens. Now, if you're a designer in these marketplaces, you are trying to look for a job, the platform says, oh, these two companies are looking for a logo. You say, great, I'm going to produce a logo for the Italian bed and breakfast. Well, a transaction does not really yet happen. Now you need to produce the logo, and then the owner of the bed and breakfast needs to like the logo. If she doesn't like the logo, then there's no transaction happening. So in retail, we have what we say one-sided preferences, which means customers have preferences over products, but products do not have preferences over customers. Whereas in matching, they're two-sided preferences. So basically, both sides have preferences over the other side. The designer has preferences over the companies that she's going to work for. And similarly, the companies have preferences over the type of logos or CVs that they received. And the research question that we have is, does the presence of two-sided preferences have any fundamental implication on the design of online assortment algorithms? So we know that from the modeling point of view, there is a significant difference, one-sided preference versus two-sided preferences. However, will that difference translate into something fundamentally different from the point of view of the algorithms that we deploy? Or can we just simply use the algorithms that are used for Nordstrom or other online retailing companies and apply them into these markets? So that's the question. Question so far?
Yeah, I had a quick question, Daniela. So do you also sort of consider capacity constraints? So like everyone can buy the same t-shirt, but a designer can't work for 100 people at once?
We do incorporate them, and yes, so you can assume that there's some sort of capacity constraints. Definitely on the side of, point of view of the people who, the owners of the companies, we just assume they can accept a limited number of them. They cannot match indefinitely. Same on the customer side, you can incorporate capacity constraints as well. And that's a great point. Good. Any other questions? Okay, so the contributions are sort of twofold. So on one hand, we have more like the conceptual contributions, and we ask, is the online two-sided assortment problem different than the one-sided one? When is the case, and why is the case? So we propose a model to study this problem in matching platforms, and there are sort of two things that matter. It's basically the fact that what we call suppliers, what is the timeline in which they're making their decisions, and the fact that they have choices make these two problems different. And then from the algorithmic point of view, we ask, okay, now that we know the problems are indeed different, how do we design better algorithms for matching platforms? And what we show is that we can use the knowledge about suppliers' preference to design better algorithms, and that the performance of our algorithms will depend on the structure of these preferences. Okay, so now let me jump into the model, and feel free to pause me and interrupt at any time. So we have a platform, in this case is this design crowd, and we have two sides of our market. We have our customers, which are going to be the designers, and we have the suppliers that are going to be the companies looking for a design. On the customer side, we are going to assume that they arrive online. So they arrive one per period, and the platform shows them something, and then they match requests. So what we are going to assume on the customer side is that they have a type, and the type has two dimensions. The first dimension is a choice model over supplier sets. So that means if I show them this supplier set, what's the probability that they will make a match request with each of the suppliers, and the probability that they will make 0 match requests. And then they also have a set of attributes that will determine their value for each supplier. On the supplier side, we are going to assume that suppliers arrive, stay for some periods, and then they depart. So think about these companies. They come, they post their job opening or their design contest. They stay for a week or so, then they see who applied to them, they make a choice, and then they leave. The type of our suppliers is also going to be two-dimensional. It's going to have first a choice model over customer set. So that means if I got this set of requests, what's the probability that I will choose each of them versus the probability that I will just leave unmatched. And also they have attributes that determine their value for the customers. Good, so just to pause for 1 second and draw the parallelism with the usual online assortment optimization problem. Here, the suppliers, what we call suppliers, will be items. And what we were adding over this set of items is basically the fact that types are two-dimensional to accommodate the two-sided preferences. So whatever I underline on the type is what we are adding. The fact that suppliers have preferences over customers, and customers also need to have some attributes to determine how valuable they are for the suppliers. I'm going to make some assumptions. The first assumption is that preferences are exogenous. So what I mean by that is that preferences will not depend on my algorithm per se. And then we're going to make some monotonicity and diminishing returns over the supplier choices. Just that means that customers, we are going to assume them to be weak substitutes of each other. And finally, I'm going to assume on the customer side that the static assortment problem is efficiently solvable. What I mean by that is that if you give me some weights for the suppliers and then I want to just show something to my customers so as to maximize the probability that they click or they click on something, or they maximize the probability of sell in this weighted version of my problem, that I can solve efficiently. If you cannot, then if you can approximate it to some guarantee, you just shave a constant from whatever I am saying next.
Sorry, are you allowing a customer to make an offer to more than one supplier?
I am, as long as you can efficiently solve that problem. But yes, I am allowing. You can make as many match requests as you want. Okay. The only important thing I would say is that this is why it might be better suited for these design platforms, is that as long as you make a match request, you are committed to matching. What I mean by this is like in these design platforms, if I make a match request, I submit a logo. So if the logo is accepted, then a match happens. Whereas if you think of Upwork, that I might send 100 CVs, but of course I cannot accept 100 jobs, then I might have a problem. But that's the only assumption.
Okay, thank you.
So what happens if you do get kind of this tied match?
Sorry?
Yeah, sorry, I've said that badly. So suppose you do submit multiple match requests and multiple of those are taken up. I mean, can that happen in your model? And if so, how do you resolve the ties?
So if you get matched multiple times, it's okay as long as you're willing to perform the multiple jobs.
Oh, I see. I'm sorry. So it's just additive.
Yeah. Exactly.
Thank you.
So that's a great, So let me now show you a bit more the dynamics within each period. Maybe this might be a bit more clear now. So within each period, this is what's going to happen. So I'm going to assume a finite horizon. The period then starts. Then the customer corresponding to that period arrives, and new suppliers may or may not arrive. The platform will see the type of the current customer and also what is the set of suppliers in my platform, and will choose a subset or an assortment of suppliers to show to the customer. The customer sees the assortment and chooses one supplier to send a match request to. And then also suppliers that are departing in that period, they see the set of requests they have received, and they decide whether to accept one or not. If they accept at least one, we say a match happens.
do the customer need to accept to, do they have like a response immediately once they submit the request?
That's a great point. In the model, in the general model, they do not have an immediate response. The only thing that we are going to assume with the customers is that they sort of make the choice to issue a request, and then they just wait to see if it's accepted or not.
And it could be accepted later on, not?
Yes, exactly.
And if it's accepted, let's say at the end of the time horizon, they will still, you know, get that job or get matched to that request.
That's correct, yes.
Okay.
So think about submitting a logo. You submitted it before the deadline. The deadline might be a week from now, but you know, if your logo was selected, then you won and you got matched.
So when the customer is choosing, I guess at each time to choose a supplier and send a match request, does their choice depend on how many open requests they have, like outstanding requests they have, or is it independent of that?
So we are going to assume that the choice, so assume that customers cannot see how many outstanding requests the others have. So in a way, we are assuming that it's exogenous to how the algorithm. However, based on how many outstanding requests they have, the platform will choose to show you something different, right? So what they show you will depend on how many outstanding requests there are, but what the customer chooses, no, we just assume it doesn't. Good. Okay, and the platform's objective is to design an online algorithm to maximize the expected number of matches in this setting. Good. Questions about the model?
I have a question. So are the customers of the same type, meaning their other preferences following the same distribution or not?
No, so that's a good point. We are going to assume that customers are, you know, they are of course unknown, and they can be what we call stochastic. So they can just follow some distribution, or they can be completely adversarial. So we are not assuming anything about what's the future arrival of customers. Okay, so good. So just one more thing about the model. Of course, there are many other things that we can accommodate, including issuing multiple requests or everything. Just for the purpose of the talk, think of customers issuing at most one request and suppliers accepting at most one of the requests they have received. But we can, you know, everything that I'm saying extends to the case where you can, both of them can issue multiple with the caveats I mentioned before. Okay, so related literature, there's of course a lot of related literature. I'm just going to touch on two papers. So this is related to roughly online bipartite settings and you know, online bipartite matching. So in online bipartite matching, just to use the terminology I'm going to use here, we assume that one side of the market, which I call suppliers, is fixed, and the other side arrives online. So the pioneer paper here was this online matching paper by Basirani in the 90s, where basically they assume that there are no choices. That means every time a customer arrives, the edges are revealed, and once the edges are revealed, the algorithm can choose to match the customer with whoever is compatible. But basically, the algorithm is choosing the match. The customer cannot really say anything about the match or not. Then there's this paper in 2014 by Golrasai and co-authors, which extend that to add customer choices. So that means that now when a customer arrives, you show them an assortment, and then the customer chooses to buy something or not. What we are trying to do is to extend that setting to a setting where you have both customers and supplier choices. So incorporating the choices on the other side of the market. Okay, so now let me move on to the conceptual part of the contribution, which is where we ask the question, when is the online two-sided problem different than the one-sided one, and why? So when is matching different than retail? And so building on what Omar was asking before, let me just talk a bit about the importance of the timing of the feedback. So imagine a very different setting, an alternate setting, which we call a setting with immediate supplier feedbacks that goes as follows. Immediately after receiving a match request, the supplier needs to accept or reject. and this decision is irrevocable. If the match is rejected, the supplier stays in the platform. If it's accepted, then the supplier and the customer leave. It's not difficult to see that, if we are in this setting where supplier feedback is immediate, then the two-sided problem is equivalent to the one-sided one. So we can map it back to the one-sided assortment case, which means that we can use basically all the algorithms that were developed for the retail in our matching problem. However, in many settings, enforcing this immediate feedback is not realistic. So if you think about online labor platforms, typically these job openings or design contests have deadlines and no decision is really made until the deadline. So for the rest of the talk, let me just focus on this delayed supplier feedback setting, where basically means that suppliers will collect the match request until the deadline, and then they will make a decision immediately before departing.
Sorry,
yes.
Can you say a few more words about why it reduces the one-sided case? Is it because there aren't costs for rejection or costs for sending offers?
Oh, I think the way you should think about it is, in a one-sided setting, I show you items, and basically your choice model tells me what's the probability that you will choose this item, each item, right? In a two-sided setting, now what's the probability that a match happens is the probability that you chose them and then they accept it. So in a way, you could just simply scale back the customer's model by multiplying by this probability. And so that's the idea.
Are the deadlines public information?
Sorry?
So do both sides of the market know the deadlines, and do they factor the deadlines into their decision, or only the set of people?
I think for the supplier setting, it doesn't really matter because they have no control over the process until the deadline. For the consumers, we are going to assume that they do not necessarily see the deadline, or even if they see the deadline, they don't really have any information about who has applied, so it's immaterial in a way.
Oh, because it's not in equilibrium. Okay.
Right, yeah, it's not an equilibrium. That's why I say it's exogenous. Sure. Yes. Okay, so now that we have that out of the way, we are focusing on this delayed setting. Let me just introduce one piece of notation, which is very important. So our objective is to maximize the expected number of successful matches. And let me just introduce this term over here, this WI of C, which means the probability that supplier I accepts any request when the set of requests is C. So I got, the set of customers that want to match with me is C. What's the probability that I will accept any of them as opposed to matching outside? So some examples that you can think of, if you think about a matching or a retail setting, then this WI of C will be basically the minimum between 1 and the cardinality of your set. So if you didn't get any requests, you match with probability 0. If you got one request, you match with probability 1. In the multinomial logit setting, well, it will look basically as the multinomial logit. So you're going to basically sum over the qualities of everyone who's in the set divided by 1 plus the sum of the qualities of everyone who's in the set. So I just normalize out the outside option to be 1. So then we can express our objective function as basically the sum over the set of suppliers of the probability that they will match given the set of requests that they have received at the end of the horizon. Okay, and this is just because I am only going to I'm going to show only suppliers that are still in the platform. So once the supplier leaves, the set of requests that they received does not change. And here, of course, we are going to take the expectation over that, and the expectation here is going to be taken with the set of requests that they have received. So this is going to be a random set.
Can I ask a question, please?
You can, of course.
So QIT is the preference weight of supplier I to customer T. Is that right?
That is absolutely correct.
Yeah. So do you handle like the case where, WIC could be, a general reward function, or it needs to be a probability between 0 and 1?
It can be a general reward function. That's a good, just for the purpose of the talk, think of it about the probability. In general, it can be a general reward function. So it can be revenue weighted, whatever you want, as long as it satisfies monotonicity and diminishing returns.
And what is diminishing returns?
Conceptually just means that customers are weak substitutes of each other. Mathematically just means modularity.
But under MNL, the thing is not going to be, I mean, in general, the revenue function is not going to be submodular, right?
If it doesn't satisfy modularity, then we cannot, nothing that I'm going to say here holds, but it's okay that it doesn't hold. I'm happy to talk more about this.
Sure, sorry.
Yeah, I mean, even if it, yeah, happy to talk more about this. Okay, so the benchmark we are going to be using is the Clairvoyant benchmark, which we are going to assume that knows the sequence of arrivals and it knows the sequence of how suppliers are going to come and leave, but does not know the realization of the customer's valuation. So it doesn't really know what are the choices. It only has this probabilistic knowledge about how they're going to choose. And the performance metric we are going to be using is that of competitive ratio, which is the worst case ratio between the expected number of matches in the solution found by our algorithm and those in the clairvoyant solution. So we just take the infimum between time horizons and between arrivals of customers, arrivals of suppliers, of the ratio between the matches in our algorithm and the matches in the clairvoyant. Any questions about this? Okay, so now let me talk about the greedy algorithm, which is the first algorithm that we would all analyze. So greedy algorithm, what does it mean in our setting? Where we are going to show to each incoming customer the assortment that maximizes the expected increase in number of matches. So basically what we are going to do is we are going to choose the assortment that maximizes the sum over all suppliers in the assortment. If this specific supplier I is chosen, then we just compute the increase in number of matches. The increase in number of matches is basically how does the matching probability of that supplier changes if I add the current customer to the set of requests they have received so far, minus the probability that they already had by the set of requests they have received so far. And the expectation here is just going to be taken with respect to the choices of the customers.
Actually, quick question about the clairvoyant.
Yes.
If you only care about the number of matches, why not let everyone, like every customer, be visible to every supplier, like every buyer at that point, and then just find the maximum matching? Or I guess my question is it obvious that the clairvoyant is more complicated than just allowing full visibility and then allowing for, especially because you have a monotone function? Isn't that just always the optimal?
I guess the question would be, how would you, I mean, if you allow, imagine that you have a supplier that it's very good and everyone likes it, and then a set of mediocre suppliers. If you allow visibility of all suppliers, everyone that comes will send a request to the good supplier, right?
I think
I'm saying everyone sends requests to everyone. Oh, like since the weights don't matter, since only matches matter, is that not optimal?
So I'm guessing if you have a setting where everyone can set requests to everyone, then of course, sure. But typically when we think about these choice models, think of this as you can send multiple requests, but you have some either implicit or explicit capacity on how many requests you can send, right?
I see. Got it. Okay.
So that, I think it's the more complicated part.
Yeah, that makes sense.
I think, so there is one fundamental point here. So does the clairvoyant knows the choice of the customer, or like just the choice probabilities?
Just knows the choice probabilities.
I see. Okay, thank you.
If not, basically you can show that the competitive ratio can be arbitrarily bad in general. Okay, so one thing that we can show is that the greedy algorithm achieves a competitive ratio of 1/2. And this, of course, is not too surprising because 1/2 is the competitive ratio that this algorithm can achieve in related settings. However, in related settings, including online matching and online one-sided assortment, you can construct better algorithms. In our setting, you cannot. So you can see that there's no efficient algorithm that's more than half competitive for our problem. when suppliers have rank-based preferences. So what does that mean is that this two-sided setting is not only a generalization of the one-sided problem, but it's also in general harder to solve. So I want to give you an intuition why. Before doing that, just let me note, I'm assuming that arrivals are adversarial. If you assume that they're stochastic, the same happens. You get a better competitive ratio, but the other settings also do better. So the same intuition happens. So what makes the two-sided problem harder? So let's start with the graph I had before, where we start with this seminal work by, Basirani of online matching. Well, if we think about the offline version of this problem, it's the max weight matching, which is an easy problem to solve. And they show that they can achieve a 1-1 over a competitive ratio. This ratio is tight. And basically the hardness here comes from the fact that you don't know who's coming next. So you don't have visibility into the future of your arrivals. If we look at the one-sided assortment problem that adds the customer choices, they basically obtain the same competitive ratio, at least asymptotically. And here the hardness essentially comes from online matching. So that means that if we add customer choices into the problem, we are not really making the problem harder. Now, there's this other work by Capra-Love and co-authors that's called online welfare maximization, which is an online matching setting where now you can assign multiple customers to suppliers, and suppliers have valuations over a set of customers. So they have valuation functions. And they showed that half competitive ratio is tight with coverage valuations. And the hardness here comes from two parts. The first one is even the offline problem, even if you know who's coming next, that problem is hard to approximate. And then you add the online nature to it, you of course are making it harder in a way. And our setting basically inherits the hardness from that problem. We have a half competitive ratio, it's tight. And the way we show it is basically by showing a mapping between coverage valuations and rank-based preferences. So what are the takeaways here? The takeaways is that this problem is indeed harder than the problem for retail. And what's making it hard is the fact that suppliers have delayed decisions, and also the fact that supplier choices can be general. The uncertainty, however, associated to the fact that customers have choices does not really make the problem harder. So if you think about which side of the market is driving my hardness, well, it is the supplier side. It's not really the customer side. Okay, so that concludes the conceptual part of the talk. Let me now focus on the more algorithmic part of the talk. We know that there's now a difference between these two settings. What can we do to construct good algorithms? So we know that nothing can be less than greedy when we have general supplier preferences. So what we are going to do next is we are going to restrict the class of preferences of the suppliers, and we try to understand how does the structure of these preferences will affect the performance of our algorithms. Okay, so the framework I'm going to be using is that of balancing algorithms. How many of you are familiar with balancing algorithms? Okay, so let me just explain the idea. It's a very simple idea. We didn't invent it. It existed in the literature before, and it's very simple. You want to sort of, in a way, trade off the immediate rewards of whatever you're doing with these customers versus your opportunity costs. So versus the potential rewards that you might get from future arrivals. So if you think about online advertisers, you want to give priority to those advertisers that have a lot of remaining budget, right? So you want to sort of give priority to them when you assign the bids. If you think about online one-sided assortment, what you want to do is to give priority to products that have higher inventory remaining, right? Because those are the ones that are going to be constraining what is the revenue that you can obtain in the future. In our setting, what you would like to do is to give priorities that are less likely to suppliers that are less likely to match given the request that they have received so far. That's very natural. How are we going to do that? Well, these algorithms operate by using what is called a balancing function. So the idea of the algorithm is as follows. What you would like to do is to maximize, to find the assortment that maximizes this term over here. The first part of this is essentially the same that we had before. It's the grid increase, the marginal increase in number of matches. But now I'm going to discount this increase by something that depends on what is the current set of requests that the supplier has. So a function of the request that they already have. Typically, these algorithms are going to be analyzed in some asymptotic regime. We call it the epsilon small probability regime, where basically each customer request has at most an epsilon probability of being successful. So this generalizes, large inventory regime in one-sided assortment and small bit assumptions in online ads. So what formally this means is if you give me an epsilon, then the instances in the epsilon small probability regime satisfy basically the probability of matching given that request is less or equal than epsilon times the probability of matching if I get a lot of requests. Sorry, I think there's a question in the chat, but I was not monitoring the chat. So I think you have a sleep. Is that a sleeping baby? Oh, sorry. Yes. So I won't make you talk. So it says a customer will have smaller probability of being accepted. That is correct. So epsilon is because we are assuming diminishing returns on the W, the probability of being accepted when you are alone is going to be more than the probability of being accepted if they're somewhere else with you. I don't know, because you have a baby, I'm now talking in a lower voice, naturally. Okay, so that's the formal definition of it. And we sort of think this might be reasonable in this setting. If you see at this design contest, basically, they do get a lot of designs per submission. Okay, so the first question we have is, can balancing algorithms beat 1/2 in the epsilon small probability regime? Why do we think they might? Well, because in this asymptotic regime, in fact, balancing algorithms with exponential discounting, so when my balancing function is an exponential function, achieve the optimal competitive ratio. So we think we might do better, and it turns out that no, it doesn't matter. Even if you assume this epsilon small probability regime, you cannot do better than 1/2. So asymptotics are not enough for us to do something good about this. So what else we can do? Well, what we are going to do is we are going to restrict the class of supplier preferences, and we're going to look at basically multinomial logit and nested logit and see what we can say about this. So what's the challenge? The challenge is how do we find the right balancing function? So the balancing function is the only thing that we are creating in our algorithm. The rest of the algorithm is fixed. How do we find the right balancing function? Well, basically we use our knowledge of the supplier preferences. So let me show you that. So we are going to be looking at nested logit preferences, which just means that customers are divided into nests. So let's say experienced designers versus unexperienced ones. And then the supplier choice process is basically two-stage. The first thing that they do is they pick a nest, and then they select a customer within that nest. So there's a nice way of parameterizing this based on what's called a nest dissimilarity parameter, which is a parameter gamma between 0 and 1. And the functional form of this will be the one you see there on the bottom. So basically, my probability of matching given set C is going to be the sum over the nests. And then within each nest, I sum the utilities of everyone in that nest, and then I just take the power to gamma. So this over here. So let me just make two observations. The first one is if I take gamma equals to 1, this is just a multinomial logit setting. Okay, this is a manner. What happens if I reduce gamma? So if I take small gamma, just think of gamma being very small, then what I'm doing is I'm adding more competitions between customers in the same nest. So making them closer substitutes to each other. So if gamma is very, very small, the first customer in my nest will give me a lot of bump in my utility. The second customer really not much. Okay, so just let me start with the case gamma equals 1. We have an M&L balancing function. One thing I want to mention is we are assuming the small probability assumption, but within small probability, we are allowing for the weights to be sort of arbitrary. We are allowing for different suppliers to have different weights for different customers. Okay, so we are still assuming heterogeneous customers. And they can be orders of magnitude different as long as everything is small. Okay, so this is the main theorem. Let me just present the informal version of the theorem, which says as follows. Suppose that we can construct a balancing function that satisfies the following ordinary differential inequality for all x. Then the resulting balancing algorithm, which we call preference-aware algorithm, asymptotically achieves a competitive ratio of kappa in the epsilon small probability regime. So let me digest that. Why are we calling this preference-aware algorithm? When we are designing this differential inequality, we are strongly using the fact that supplier preferences are follow a multinomial logit. So that's where this part comes from. And then kappa, the competitive ratio, shows in the right-hand side. So naturally, as you increase kappa, it is less likely that such a function that satisfies this inequality exists. So at some point, basically nothing will exist. Okay. So that's nice. So this sort of gives us a sufficient condition to obtain a competitive ratio. If we were to have one function, we can test for which kappa it satisfies this condition, and this just gives us a competitive ratio. What we also do is we provide an algorithm which is efficient to construct this preference-aware function.
Quick question.
Yes.
What does it mean to be asymptotically achieving a competitive ratio?
So the way you should think about this is that the actual competitive ratio will be the square root of kappa minus an O of epsilon. So as epsilon goes small, I get closer and closer to kappa.
Okay.
Make
so
sense?
It's asymptotic in epsilon and not in like the number of suppliers or customers?
Implicitly the small probability assumption assumes that you have a lot of customers.
Oh, I see.
But not in the number of suppliers. The number of suppliers does not play a role.
Okay, cool, thanks. And one more question.
Yes.
Do you have a restriction on the range of x in this equation inequality here?
Yes, x needs to be between 0 and 1.
Okay, thanks.
That's good. Okay. And well, of course, we can extend this to nested logit. You can see that it's basically the same idea. We also get this nonlinear ODI, which is very ugly. You can see that it depends on gamma, our nested similarity parameter, and yeah, sort of generalizes the previous result to nested logit. And we want to ask what's the effect of gamma on performance of our algorithms. But before I do that, I want to give you an idea of the proof if I have time. So the proof idea here is a decomposition approach. So typically the way you would think about proving things here is typically you use a primal dual approach, or you would do something like trying to bound the value function. Well, this is a bit different. I like to call it's a first principles proof, but it's not quite. So let me show you the idea. So the idea is as follows. Let's fix, a function that satisfies our inequality. Let's fix epsilon to be small enough, and let's fix the arrival patterns. Okay, so once I fix the arrival patterns, then I'm just going to let my algorithm run with these arrival patterns, and this will generate some random set of match requests. So what I'm going to do is I'm going to fix an arbitrary coupling of this sequence of customer requests under both my balance algorithm and the clairvoyant algorithm. And basically what we want to show is that this ratio over here is greater or equal than 1 minus epsilon, or something that depends on epsilon, times kappa. I'm basically showing that this ratio over here is greater than this number, just corresponds to showing that the sum over my supplier set of the probabilities that they match at the end is, is greater than this. And basically that's the quantity we want to bound. So we want to bound the probability that they match at the end and just take the expectation over this coupled stochastic process. Okay, so my first step in this is going to be this decomposition approach, where basically what we are going to try to do is we are going to lower bound these quantities of interest. Sorry, I'm having troubles. If you see me hesitating, it's because I am having troubles. I cannot see my laser pointer. I'm guessing you cannot see it either, right?
We can see your mouse.
Sorry?
We can see your mouse.
Oh, excellent. Good. Okay, perfect. So what I'm trying to do, that's even better. So what I'm trying to do is I'm trying to bound this quantity over here, the sum of the suppliers over what's the probability that they are going to be matched at the end, given by basically my set. And I'm taking the expectation over all the couplings. And what I'm going to do is I'm going to decompose this sum. I'm going to lower bound it by the sum over the supplier set of these quantities Ri that basically will depend only on things that affect the supplier I. So that's why I'm decomposing this into things that only affect one of the suppliers. And of course, this is a very messy expression, but it does have a nice intuitive interpretation, which is essentially the sum of two terms. The first term is this discounted payoff of the clairvoyant algorithm in our sequence. So that means I'm going to take my sequence of customer requests, but at each step I'm going to think, okay, what will the clairvoyant show? What will be the choices under this show? And basically what will be this discounted payoff that I would get? And then the second term is basically what's the total discount that I accumulated in my own sequence. So how much money I saved for my bad decisions, how much my discounting applied. Okay, good. So now that I have decomposed my quantity of interest into these little thingies that depend only on each supplier, we want to show that for every coupling and every supplier I, this inequality holds. And if this inequality holds, then I'm good to go because this is basically going to imply my result. But as I was telling Sid before, this is sort of a very strong thing to show, but let's see. So I'm not, the proof from there onwards does include a lot of algebra. I just want to show you what's the intuition. So then we're going to do next is to find a lower bound for these Ri's. So for the first term, we're just going to use the multinomial, the fact that supplier preferences are following an MNL. And this is where basically it manifests that it follows an MNL. For the second term, we are just going to use the continuity properties of my function and just obtain this bound. So if we combine the above bounds, we just get that the expression of interest is lower bounded by this. And now we are basically going to take the infimum over what will be the match probability in the clairvoyant sequence. Luckily for us, we can solve this in closed form. So we get this nice expression over here. And this nice expression over here looks a lot like my differential inequality. And then we just use the fact that F satisfies this inequality for all X, in particular for this X. And then we just obtain the result that we wanted. So I just wanted to highlight two things. If we want to generalize this to nested logit, well, we will face two challenges. The first one is instead of MNL substitution patterns, now we have nested logit substitution patterns, which are sort of harder to deal with. And the second thing is that when we take this infimum, it's also harder. Okay, so now let me, in the 5 minutes that I have left, I have 5 minutes again. Good.
Yeah, about that.
5 minutes that I have left, let me show you some insights. So here I have the best possible balancing functions as a function of X. And here we have for different settings. So I told you, if we look at one-sided assortment, they use an exponential disk balancing function. you can see that if we have suppliers have M&L preferences, our balancing function is not only not exponential, it is concave. It's like the opposite of exponential, right? So let me first share the good news. Good news is that if we use balancing algorithm with this plotted function, we can get something that is better than 1 minus 1 over E, even if adversarial setting. So that's sort of nice. And now let me comment on the differences in shape. What are they used for? And the idea is that if you think about one-sided assortment, the reward that you get from a successful allocation, basically from selling an item, is independent of previous allocation. So if you sell an item, you get a revenue, and that's independent of who bought the item previously. Whereas our setting, we have these diminishing returns, right? So the more allocations or the more match requests somebody has, the less reward that the following gives me. And it turns out that greedy is already partially accounting for this discount when it optimizes over the marginal increase of matches. So basically, in a way, greedy alone without the discounting is doing part of the balancing. The other thing I wanted to comment on is what is the effect of the nest competition on performance. So here we have the competitive ratio guarantee for different functions as a function of gamma. Remember, gamma is the nest dissimilarity parameter. 1 is multinomial logit. As I decrease gamma, I have more competition with its customers in my set. So here we have the competitive ratio guarantee for what happens if I use an exponential discounting, what happens in red if I use a multinomial logit discounting, and what happens in black if I use the optimal discounting. So for every gamma, I found the optimal function and I just used that. So there are sort of two takeaways from this. The first one is that preference awareness matters. So you cannot simply use for all the preference the same discount function because you are going to be leaving something on the table. So there's a value of just tuning your balancing function to the actual preferences of the customers, the suppliers, sorry. And the second takeaway is that substitutability within a nest hurts. So you can see that as gamma decreases, the competitive ratio guarantee goes to basically a half. So here I have the best possible balancing functions for different gammas. We start in red for the multinomial logit, and you can see that I am just decreasing gamma, and when gamma equals 0.2, this is almost a flat function. Flat function is basically there's no discounting or there's a uniform discounting, which just means I'm going to be using the greedy algorithm. So that's sort of not surprising that the performance converges to half. And in fact, we can show that no deterministic algorithm, and in particular no balancing algorithm, can do better than a half as gamma goes to 0. Okay, so let me sum up what have we learned. So what we have learned is, if you think about the online one-sided retail assortment problem, the algorithms there you can construct are 1 minus 1 over E competitive, and that is the best possible regardless of what's the choice model that you assume for the customer side. If you think about a matching setting, then depending on the supplier preferences, you can do better than 1 minus 1 over E. If you assume general supplier preferences, half competitive is best possible. So what this means is that essentially assortment optimization for matching markets can be easier or harder than for retail settings, and that strongly depends on what's the preferences of the suppliers, how do they look, and what's their shape. The other thing is that balancing algorithms with exponential discounting are widely used in practice, and what we are trying to do in this work is just, well, let's rethink balancing algorithms for matching platforms and how to find the right balancing functions. Perfect. So thank you so much. Any questions or anything?
Maybe I just go back to the point that I asked about, and maybe I have the answer, or just correct me if I'm wrong. So when you say suppliers has an M&L model, so what you're taking into account is just the, the W is just the 1 minus the no purchase probability. Or do you associate, like can you associate, a reward for each, for each customer, and just use the standard MNL model where, in the denominator, you won't have that QIT. You just like have, in general, sum of RIVI over 1 plus sum of VIs.
So this QIT is in general what you're saying, right? This is, in a way, the revenue that the supplier will get from matching with customer of type T, from the Tth customer.
I think this is the purchase. This is just the probability of getting matched.
Yes.
The sum of the utilities over 1 plus the sum of the utilities.
Yes.
And that's, I think, in that case, that's what could guarantee the submodularity of, that's the submodularity of WC.
Yes.
Yes. I was just, thinking whether you could handle a model where, you have, for each customer, he's going to associate, a reward, or like, let's say the price that's the customer is going to pay for him. Each supplier is going to associate a reward RI. And then you will have like the WIC would be just the revenue that you will get from your choice set. And in that case, the numerator would be sum of RI, VI, and the denominator would be just 1 plus the sum of VIs. You won't have like the same term in, so that revenue is not going to be a probability. I'm not sure if I express well myself. If not, we have the 30 minutes to talk tomorrow.
Yes, we can talk more tomorrow. Just let me say something. You can handle revenue. So we could weight this by a revenue of the supplier. That is going to be totally fine. If you're thinking about doing revenues of customers and suppliers, this will be more like an edge-weighted matching problem. And, this is a very, very different kind of problems.
Okay.
If that makes sense. Any other questions?
I'm curious, like, what about the supplier MNL makes this easier? Is it like doing some like natural balancing, or?
I don't have a good answer to that. What makes it easier, it's basically the shape of how concave is. So there's like the curvature of the function, of your choice function, is basically makes it easier. I'm happy, in general, when you have these concave returns, the harder is basically what you would have, like a straight line and then flat, which is your online matching sort of revenue. That's the hardest. And the more concavity you add, it's typically better. So that's what making this is just how the curvature of the function.
We have one more question. So in the online one-sided assortment, so the 1 minus 1 over E is the approximation. I think it could be improved if we are not assuming an adversarial model, like if you're assuming like IID arrival of customers. Can you say anything about this setting?
Yes. So what we get in that setting is that we have a 1 minus 1 over E, and here. So greedy is half competitive, is 1 minus 1 over E competitive under stochastic arrivals, but that's the best possible. And as you say, even if you have a online matching or online one-sided assortment, when you have stochastic arrivals, you can do better. So conceptually, the same order of hardness remain, if that makes sense.
Okay. Yeah. Thank you.
And I'll maybe read out.
As is awake now, I can ask. I was wondering what changes if there's history in the system. So suppose the customers arrive repeatedly, so that you can is there? Well, I guess I was wondering what do you think would change in the results if if you could try to learn preferences from past actions of the customers?
That's a great point. So typically, the setting you are describing is a bit closer to what we call the stochastic setting. In a sense, in the stochastic setting, the same customer does not arrive repeatedly, but a customer the same as the one now arrives with some probability in the future. So in a way, you should think of each arrival at each point in time comes from some probability distribution. So if you assume stochastic arrivals, and this I'm going to be very informal, and sufficiently long horizon, then basically people have shown in related settings that what you can do is you throw up, you're learning about the preferences of these types, or what are the types in your distribution set for the first couple of periods. You throw the revenue there and you just exploit for the next.
I see. So, but you assume that the types are observed, but the utilities are not named.
That's correct.
Mm-hmm.
Yeah, that is correct. That's sort of.
I guess if you didn't, if even the types were also unknown, you'd have to. That would be much trickier, right?
Yes. So if the types were unknown, I guess what will happen is more or less what I was just saying. I'm happy to talk more about this, but basically, if customers were to arrive repeatedly in the future with some probability they will show up in each period, then you could try to do something like that.
I see. Thanks.
Learn for the first couple of periods and then exploit in a stochastic setting.
Mm-hmm.
So I think I missed one thing about the assumption. So when a supplier makes a decision and chooses a customer, all the other customers who applied to that supplier, they're not allowed to reapply to a new supplier?
So we are assuming that they do not reapply.
Okay, got it. Okay, so then, yeah. So then I guess my question is, what do you think would happen if you had that sort of a recourse decision? So like, do you think, again, it would reduce back to some kind of a simpler one-sided setting where you were allowed to, like, a customer was allowed to reapply if the corresponding supplier rejected that customer?
That's a good point, and I don't know exactly how. That's a good point. It's, you are very well aligned with our referees want us to do now, and I'm still trying to figure out what is the right benchmark there to compare against. It isn't. I mean, it is unclear. In a way, you are giving more power now for customers who were rejected to come back. So you would expect that will mitigate the impact of your bad decisions. So your competitive ratio will go up, right? But it will depend also how much power are you going to give your clairvoyant. So if you give your clairvoyant too much power, the competitive ratio can be arbitrarily bad, if that makes sense. So now it's a great question. It's an open one, and it's very hard to come up with a good benchmark that it's meaningful and analyzable and everything. Because at the end of the day, what you're doing there is you're introducing some endogeneity in your arrival process, right?
I mean, yes, but okay, by the way, just to be clear, I'm not the referee. I'm a bit scared to ask questions. But no, I guess I was now thinking that if I had a recourse, I could visualize the problem from the supplier's side, and I could think of suppliers as arriving at their deadline. And like, this is me thinking for a minute, and so this may be complete garbage, but it felt like Carvazirani from the supplier side. But I don't know if that's true or not. Like, basically, since there's recourse, I might as well wait for each supplier's deadline and then bring in the supplier, try to match them to all the consumers who are waiting, and continue.
I'm not sure.
We should take this offline. I think,
Okay,
I haven't thought enough about it.
Otherwise, let's thank her again.
Thank you so much, Nikhil, for the invitation, and everyone for attending.
Yeah, this was great. Thanks.
Thank you.